Hello everyone, here's a new video and it's going to be about electricity. What exactly or how exactly does it work? No one really knows what electricity is, but we do have equations and all kinds of ideas about how it works. So with electricity you mostly hear about voltage and sometimes you hear about amperage, current and resistance. So what does it do? How does it work? I'm going to explain it by comparing it to, well, flow of water. That's a very good analogy. So here I have a water tank and I'm going to connect a hose or a nozzle to it. And the lower I get in the container, the more pressure you have. If you go swimming, you will notice it also. If you just float on the surface, there's hardly any pressure on your ears. But as soon as you start diving downwards, you will notice some more pressure in there. And that's a physics class on its own. But let's take a look at this. The flow within this nozzle is depending on two things, basically. The amount of pressure, which is volts. Let me just put it in here. So the further down the nozzle goes, the more pressure you have. That's why these water towers are always up there instead of on the floor. They're just trying to put it as high up as possible. And also the resistance, which is, well, actually the nozzle diameter. If I'm just going to insert a straw here, very small, there will be less flow. I could also put a cork in it, which is in electric terms more something like the resistance of air. If I'm just holding up two wires, plus and minus, from the wall socket, it's 110 volts or 230. If I don't get them too close together, you won't have any current flow in between, unless you raise the voltage. So let me put the current in here, which is indicated as the letter I, because, well, probably from the term induction, because you induce flow from resistance and voltage. How does this relate to an equation? I'm going to show you. This is an equation. Sometimes they just show this within a triangle like so. But how does this relate? So if you would like to know the current, which I explained, I'm going to put it in front of this equation and equal sign. And what do you know? If you increase the voltage, in this case pressure, you will increase the current. If you increase the resistance, you will decrease the current, which is what this equation does exactly. The current depends on this division. The voltage is usually a fixed value, like 110 or 230 volts from this wall socket, or 12 volts from an adapter or something. With resistance, like copper for instance, you have low resistance. You don't need much voltage, like say 0.5 ohm. Even with low voltage, like 12 volts divided by 0.5, you still have 24 amps in current. That's a pretty high amount. Compared to air, for instance, where the resistance is extremely high, like a million ohm or even more, then you have to generate quite a bit of voltage to get even the slightest amount of current flowing through air. So I'm going to demonstrate that in my workshop. I'm going to demonstrate how the current increases through air if you lower the resistance. Now I have a little setup here. And this used to be a taser. And I'm going to show you current. I'm just going to turn it on. And this is about 50,000, 100,000 volts or something. As I move the gap, make the gap smaller, I'm just lowering the resistance. And then the voltage can overcome the resistance and then you have current. It's as simple as that, actually. So, if I move even closer, you can see the current increase. Let's do that. Because I'm just lowering the resistance.
So that's basically it. Another way to lower resistance is to use different materials, like for instance metals. Now you can clearly see that metal is low resistance than air. So that's basically it. Now you can see current in action.
Yeah, so basically that's it. Now there's another term, which is power. How much electricity you use. And that's actually the most important one, because that's what you see on your electricity bill. How much electricity did you use? And there's another equation for that as well. So if I, for instance, would like to make this cartwheel flow with a smaller nozzle, like so, you would have to increase the pressure to get that done. And if you don't have much pressure, you would have to increase the flow, and directly, which it means reducing resistance. But it's about the combination of flow and pressure that makes machines work. So here's another equation for that. So if I would like to know how much power any something uses, I'm just going to remove this from the equation, and then you can calculate it. If I increase a voltage, in this case pressure, you get more power. If you increase the flow, you also get more power. So this is a suitable equation as well. You just multiply them, and if you raise either of them, you get more power. It's unlike this one where if you raise the resistance, you get less current. So, but that's basically the two equations that you need. So concerning power, let's take a look at some appliance and a wall adapter and see what it does.
Now let's take a look at what we have here. This is a cable router, and it also has Wi-Fi. So this is connecting computers and stuff in a network. It's not that important to know. However, what is this connector here. If it would zoom in a bit, and this would be the power connector, little round thingy. So I'm just going to turn it over a bit further, and here I can see 12 volts input, 1.2 amps. The input says this is a machine that needs this amount of power and this amount of current to operate, and this amount of voltage, I mean, yeah. So let me find a power adapter, For instance, this connector here will not fit in that round insert that we have here. So that wouldn't work. But I know what this is. This is the micro USB connector, which is for, well, usually Android phones. iPhone has its own type of connector, of course, but Android phones use the standard micro USB connector, and they are usually USB is usually 5 volts. Let's take a look at this thing. Yeah, this is 5.2 volts, a little bit more, which is very good for charging. 3 amps and nice amount of amperages. But this is not suitable for this cable router, so I'm just gonna look further. Well, this one has the connector we need. It's called a barrel jack. It's a 6mm barrel jack, and that would probably fit. There we go, it fits perfectly. And usually these 6mm barrel jacks deliver either 6, 9 or 12 volts, or maybe even something more like 20 for laptops, for older laptops and such. Let's take a look This is indeed 12 volts, 1.2 amps, exactly what this router needs. So this would be a suitable device. However, well, 12 times 1.2 is 1.44 watts, or actually 14.4 watts. This would be operating at maximum capacity. And I don't like electronics to work at maximum capacity. I would like to have a bit more amps, because this adapter has an output of 1.2 amps, which means that's the max it can deliver. That's its maximum capacity, 1.2 amps. Let me see if there's something else. This thing also has the same barrel jack, so that's fine. And it runs at 12 volt 2 amps. So that's the maximum it can deliver. It doesn't mean it delivers 2 amps, because that's just depending on the internal resistance of what you connect it to. But it can deliver up to 2 amps. We only require 1.2 amps, so this one is pretty good. Even if it can deliver 10 amps, it won't deliver 10 amps. It depends on the resistance of the device you connect it to. So that's it. 12 volt 2 amps. This would be a suitable device. It's not at its max capacity, so it will run better.
Suppose you're walking to a store and you would like to buy a light bulb. Well, there are several types and kinds, but let's say a 50-watt light bulb, which is the P here. Well, they sell them uh, running at 230 volts, in the US 110 volts, or 12 volts, but they produce the same amount of energy because, well, the 50 watts is pretty bright. It's the power consumption, so it's also the amount of light they give off. Um, well, what's the difference? How does that work exactly? How can you have different voltages and still produce the same amount of power? Well, that's the current. So let me put this P in front here just to clarify. So on one hand, you have a 50-watt light bulb running on 200, let's say 200 volts for convenience. And then you have another light bulb that produces 50 watts at 12 volts. And let's say 10 volts for convenience. Well, they have to do something with the current in order to get the same amount of power. And how do you change the current? Then you change the resistance. So let's see how much current it would be. I'm going to move this one in front, like this. And let's say you have 50 watts for a 200 volt light bulb. Well, 50 divided by 200 is 0.25 amps of current running through that light bulb. That's the flow of electricity. Now, how much resistance would that be? I'm going to move this in front here and say 200 volts divided by 0.25 is 800 ohms. Now, 800 ohms. Now let's take a look at a 10 volt light bulb, for instance. 50 watts, same kind of energy usage, divided by 10 volts is 5 amps of current. Now 10 volts divided by 5 is 2 ohms. That's quite a bit of difference compared to 800 ohms. So that's basically it. Now let's do some trick. Let's say we connect this 10 volt light bulb to your socket, to your wall socket, that which produces, well, 230. Let's make it 200 volts and see what happens. So I'm going to switch all this back like so. And I'm going to say, well, you have a resistance of 2 ohms. You have 200 volts. What's the amount of current running through there? So I'm going to do this backwards, in the backwards order actually. somewhat like that. So 200 volts divided by 2 is 100 amps. 100 amps. You know, in fact, your fuse box would blow. In the Netherlands, where I live, we have a fuse in our fuse box that's limited to 16 amps current at 230 volts. So okay, let's get back there later if I ever want to. So the amount of current is set. Let's find out how many watts this would produce if the light bulb wouldn't die already. So okay, so we have 200 volts and 100 amps. That would be 20,000 watts. 20,000 watts. Ah, okay. You should look online for a heater that could heat up your home. They would produce maybe 2,000 watts or 3,000 watts at most. I think 2,000 watts is a pretty strong heater already. So yeah, 20,000 watts, that would heat up 20 homes. If it wouldn't blow or your fuse wouldn't blow, of course. But yeah, light bulb is not made for that. With regards to the device I've shown you, the appliance, it required 12 volts, 1.2 amps. But the thing is, I picked out a 12 volt 2 amps adapter. But that's not a concern because it still will draw 1.2 amps. Why? Because the voltage is fixed. The adapter will deliver 12 volts. It's not going to change it because you connect a light bulb or you connect a cable router. It's not going to change the voltage. These devices work on 12 volts. What is going to change is its internal resistance, like with the light bulbs I've shown you. They have a certain resistance inside, which is a fixed amount as well. So this is the part that is fixed. It runs on a voltage and it has a certain amount of resistance, and therefore you can always find out what the current is running through it. Even if you select an adapter that can provide for 10 amps, it will not produce it because the device you connect to it doesn't require it. So it's going to draw 1.2 amps, and therefore a 2 amp adapter is not going to run at peak capacity. As far as power consumption, that's what's appearing on your energy bill. What is it going to cost me? So let's see. I'm going to put the power consumption in front, like this, and now I can calculate how many watt is using. 12 volts times 1.2 amps, 14.4 watts. For our convenience, it's going to be 15 watts. Your bill is like in Europe, at least in the Netherlands, we pay like 20 or 25 cents for each kilowatt hour. So basically, if you run this device 15 watts for 10 hours, you have used 150 watts. If you run it for 100 hours, you've used 1500 watts for 100 hours. That's 1.5 kilowatt, since a kilowatt is 1000 watts, so 1.5 kilowatts. If you pay 20 cents for each kilowatt hour, you've paid 30 cents for 100 hours. So yeah, 30 cents for 4 days. However, yeah, the adapter is also using a bit of power, and some adapters run at 50% efficiency, which means that for each kilowatt you put in, the adapter is using twice as much. Yeah, that's a bit, maybe a bit exaggerated, but I might be paying 60 cents for 4 days of use. Well, up to now, I hope I've provided a satisfactory explanation of everything. Now I'm going to continue with the birds and the bees, let's say the plus and the minus. Everything in nature is balanced out. Opposites attract. So there's a plus and there's a minus and they stick together like so. And your power company is going to screw that up a bit, because what they are doing, they provide you with 2 copper wires in your wall Then there's a line or live wire, but they call it the line. And there's the neutral. As you might guess, the neutral is trying to stay neutral, but it doesn't really work out because what's happening is your power company is going to remove a couple of these from here, like this, and that's your voltage. It's an amount of charge, and now you have more plus than minus in here. And as you know, if I just remove this for a moment, opposites attract. And now these minuses here are attracted to the line here. And the more you move on this side, the greater the attraction. And therefore, if I have 10,000 volts, a charge of 10,000 or 50,000 or 100,000 volts, like you saw with the taser, at some point it even moves through air. It's so strong that these just move through air and you can actually see the current in the air. That's why I showed the taser. But now there's a device in between, and it also contains copper wires and capacitors and all kinds of electric components. And if they remove the negative here, it's positively charged. That's the plus. It moves through the device. This one is moving here. This one is moving over here. This one is moving over here. And scooting over like so. And then the neutral has to provide for this deficiency. And the neutral is drawing it from your neutral line and is going to add them from there and is trying to stay neutral once again, like so. And that's what's happening, and you have something that looks like a flow of electricity. And this would be DC electricity, direct current. It flows in one direction. You have a plus and you have a neutral, and they also indicated within a minus. However, your wall socket is not DC direct current. It doesn't have a flow in one direction. It has an alternating current, which means first you remove them here, and then you have a flow to the left. These will eventually end up on this side, like this, and the neutral will try to keep it in balance. And then your power company says, well, you know what? Now we're going to change the direction. We're going to add a couple of those negative electrons, and then the flow will be in the other direction. And that's happening about 50 times a second, so you have an active current of 50 Hertz, as they say. So, well, this basically concludes the tutorial or the video about electricity. And you're still here. Yeah. Well, yeah. Well, I suppose I can mention color coding just for the fun of it. All right, let's do that. Let's say, for instance, if you look at the 12-volt adapter, the 12-volt side, the output, probably has two wires in there, which are usually colored red for the live wire, but 12 volt has no capacity to do any damage to you, and probably a black wire for the neutral side. So that's interesting information, I suppose. And for a wall socket, it would be 230 or 110 volts. Okay. And that mostly is, well, in Europe at least, I don't know in America, but in Europe it's brown for the live wire. And it's gonna be blue for the neutral wire. So there you go. Some additional information there. Yeah. So, yeah. Still there, right? All right. Well, it could be in older installations in the Netherlands. I'm not sure about the US though, that you still have green and red wires. As I think, I'm not entirely sure, but I think that would be a green wire for the live wire and a red wire for the neutral, to make things more confusing. But that's older installation, so let's just not do that. And then the ceiling, where usually there's a light hanging there, it has a light switch. Well, then everything has changed, because then you'll, and I'm talking about the Netherlands, right? About Europe. There's probably a black and a blue wire there, which indicates the blue wire remains the same. It's still the neutral line, and the black wire would be replacing the brown wire, which would be the live wire, but then it's behind a switch, the light switch. So this wire could be turned on or off. You never know unless you measured it or unless you see a light burning or something. So that's another piece of information for you. Yeah. Yeah. Okay, let's continue then. There's a question that some people ask. What is more dangerous? Is it the current or the voltage? Because if you look at certain documentaries about police force, for instance, they tase someone with 15 or 100,000 volts, and they do fall down, they do lose control of the body for just a moment, but it doesn't really kill anyone, does it? So it seems like voltage doesn't hurt you. Well, it kind of does. It could, though, because you could have a cardiac arrest, you could have epileptic seizures. It's still pretty dangerous. However, the taser is limited in its current. It's designed that way. The electronics inside limit the current. Usually the body has quite a high resistance, like 100,000 ohms or more, or a million ohm. But if you have a voltage like 100,000 volts divided by 100,000 ohms, for instance, you still have 1 amp of current usually. So that would be, well, that could be pretty lethal actually. So the taser is designed to limit that amount of current and still deliver a large amounts of volts. But usually, if you have a high resistance, you need quite some voltage to get some current running. 12 volts, for instance, you can grab a 12 volt line and you wouldn't even notice it. So basically, yeah, you need something like 100 volts, or I don't think that 20 volts even does anything decent. But starting at 100 volts, you might get zapped, and there might be a pretty decent amount of current running through you. So it is the current that kills you, but it's the voltage that overcomes your body's resistance. So basically you need both. Yeah. So, well, thank you for watching, and be careful. Still here? Man, you don't give up, do you? Well, I have nothing to tell you anymore. Yeah. So, yeah. hmm Yeah. Okay, you're still here, right? You're still here. I think I should end this movie now, this video. Yeah, better. Otherwise, you'll be waiting forever. Yeah. Bye now. Huh? Bye. Bye.